So let's talk about ships now. Now, ships are kind of fun, because if we look at it, and this is a terrible picture, I really need to find a better one. But ships are fun because the drag is made up of three separate parts. So above the waterline here, we have air drag. And that air drag is from the frontal area, because there's a thick, stubby body and it's pushing back on things. And all of that's going to be from the air. Now, we also have the drag from under the water, and this would be from our wetted area of the water, or I guess whatever, if you want to stick this on Saturn, not Saturn, Io or something, and liquid methane. Whatever liquid fluid is touching the ship, pulling back on it. Now there is, and the reason that I have this picture here is there's one more, and it's this interface between the two. And this would be the wave drag. And so the wave drag is the actual momentum of the waves hitting the ship and slowing it down. And that's all driven by the Froude number. And the Froude number is that's the FR that we talked about a little bit earlier. It's spelled, it looks like Froude. It's, as far as I know, it's pronounced Froude. Dutch, I believe, was the scientist's name. And what the Froude number is the ratio of the free stream speed, which would be the ship speed, to the typical wave speed at the interface. And so the Froude number is calculated by looking at the free stream speed, or that ship speed, divided by GL to the half, or the square root of GL. So G is the gravity, and then L is the length of the ship at the waterline. So you have to actually go and calculate out what the contact is. There we go. And so if we look at this, what does it mean? Well, if I have a low Froude number, that's a big ship, big heavy ship, making big heavy waves. And so they're going to have a lot of pushback on it. So a high Froude number would be like a skier. Someone that's just skipping across the waves, making very little disturbance on the fluid. So reducing drag on a ship, I mean, you can streamline the underwater section, you can streamline the upper water section, but you do have these waves that you're creating that's causing a lot of issues. So how do we reduce the drag on a ship? And so if I take a picture of this, this is the USS Ronald Reagan aircraft carrier, and the way that you reduce this is with this big bulbous bulb. And you will see this on large ships. Now, as one student did put it once, this is not put on our ships to intimidate our enemies or anything like that. This is really about reducing the drag. You'll see this a lot on cruise ships also. I need to, at some point, I haven't had a chance to, I have some video of the bulbous bulb on one of the cruises that I've taken where the water's clear enough that you can see it under the water. So it's a really interesting way that this reduces the amount of wave drag on a ship. So let's take a look at this image here. Now, the green line here, and I do apologize if you're colorblind, so it is this line here. Whoever drew this picture did not take into account red-green color blindness, but this line right here, this is the green line, and that is the wave that's produced by the ship. Now, the interesting thing about waves is waves are basically sine waves or cosine waves. So we can do wave math where we can reduce the amplitude of waves. So this goes up, it comes down, it'll go up, come down, all the way off the page. And so now what happens is this bulbous bulb is under the water, it's thrust in front of the ship, it's going to produce its own wave. Now the wave starts underwater. So we have this wave that's coming, this is the blue line, the wave that comes up, it comes down, it's going to come up, it's going to come down, but that wave is partially underwater. But the more interesting thing is, this is set up that as it comes, it's coming down as the ship created wave is coming up. And so now you have this one wave on the up, this one wave on the down, and so it dampens the amplitude. And so what you do is you get this combined wave, which is this red guy right here. We have this combined wave of the two, as the one's going down, the other one's coming up, and so they reduces the natural wave quite a bit. In fact, you can see it, like just right here in this area, a huge decrease in the amplitude of the wave. So if I go and I take a look at things, you can see this line A would be data points of a main hole without a bulb. B here would be one with a bow bulb, a bulb in the front. And then C here would be if you had both a bow and a stern bulb. And then so you'll notice the design speed that is a Froude number right here, somewhere between 0.25 and 0.3. And you'll notice there's a huge reduction in the coefficient of drag from the wave just by adding that bow bulb. So now the question is, wait a second, if these things reduce drag so much, why don't I see this on every single ship? Because you'll notice bow bulbs are really usually only on very large ships. And if you look over here, the reason is, look at that coefficient of drag. Look how small that is, a coefficient of drag of 0.001. So these do reduce drag by quite a bit, but they only make sense on very large ships. Because at that point, every amount of drag is very important. But on these smaller, like a sailboat and whatnot, you're not really going to get a lot of effect out of putting a bow bulb on there.